Let me show you how to work problems with this. When I was young, I would watch Star Trek. That should not surprise you. This was the original Star Trek where they had all the cheap props. It amazed me that they would go throughout the universe to all these different cultures and everybody spoke English. You know, it seemed too much of a coincidence. And I was ready to give up on the program until someone explained to me that they had a universal translator built right into their little medallion there. And then it was fine. Then I just, oh, okay, well that makes sense. The second law is the translator between kinematics and dynamics. It's the connection between the motion, and by that I mean the acceleration, and the forces, the free body diagram. Let me show you how that works. If I have a 5 kilogram mass being pulled by a rope with a tension force of 100 newtons, and I find that the acceleration that results is 4 meters per second every second, and I ask you, how big is the friction force? Well, in this case, I'm giving you the acceleration, the kinematics, and I'm asking you about the forces. The first step, folks, I got good news. I have students all the time coming into my office. I don't know where to start on this problem. And a lot of times that's a valid thing to say. But not with a dynamics problem, not with a force problem. Never come into my office and say, I don't know how to start this problem. Every single force problem starts exactly the same way. What? Free body diagram. Free body diagram. Okay, so let's draw a free body diagram. The first force I put on any diagram is the weight force, straight down, earth on the block. Now this is a 5 kilogram block. The earth pulls on every kilogram 10 newtons worth. How many newtons is that pulling down on that block? 50 newtons. 10 per each. Okay? Then I ask myself, follow the recipe, ask myself, are there any magnets in this problem? No, not yet. Greg will get to it. So what touches the block? Well, the rope, and it pulls. So I get one force, period. The only thing other than the rope that's touching the block is the floor. It's not a rope, it's not a thread, it's not a chain. It pushes. Whenever one thing pushes on another, I always have a normal force. I may also have a friction force. In this case, I'm looking for how big that is, so I assume it's there. Now, just like the first step of every force problem is always the same, so is the next step. Every time you finish a free body diagram, you get to use Newton's second law twice. Once in the y direction, once in the x direction. Well, let's do it first in the y direction. That's the acceleration. How much of that vector is in the y direction, the up and down direction? None of it. And so if I come over here and do this in the y direction, that's 0. And that means in the y direction, my diagram has to scream balance, 0. I have to have just as much force up as down. That tells me the normal force is 50 newtons. Now in the x direction, it's not balanced. This force is bigger than that force because the diagram's got to scream that acceleration. Okay? Well, the question is, how loud should it scream to the right? How loud should it scream? And that is answered by Newton's second law. The scream has to cause a 5 kilogram mass to accelerate at 4 meters per second squared. The scream has to equal 5 times 4. The scream has to be 20 newtons to the right. Now that doesn't mean that this rightward force is 20 newtons. It's not. It's 100. That means I've got to have 20 more newtons to the right than I've got to the left. What's this friction? 80. Now that's the way I solve problems. Now some people don't like to do it that way. They don't want to talk about the scream or they use their gut. They'd rather use math. So let's do that. The net force is just the sum of all the forces. You add them up. And since I'm doing it in the x direction, I add up the forces that are in the x direction. Well, Greg, your mouse says you're adding them, but your PowerPoint says you're subtracting them. No, it doesn't. I'm adding them as vectors. And because this one's to the right, I add it as a positive number. Because this one's to the left, I add it as a negative. Okay, so I'm adding the vectors as I would add, I'm adding the forces as I would add vectors. Because they are vectors. Now if I just plug and chug, 100 minus f is equal to 5 times 4. You just grind away at that algebra and you get the same answer that we got, 80. Okay? Now, if that seems trivial, it's because it is trivial. And I wish that I could say it's going to get harder. Because they'd pay me more. But that's it. That's Newton's second law. We're going to do that with problems that look messier. We're going to do that with problems that have more complicated algebra. But we're always going to be working that problem right there. Now, here's your homework. It's like your homework. In your homework, you have a sled that has a mass of 30 kilograms. This one has 15 kilograms. You can fix it. If we pull on this sled with a rope with 100 newtons at 37 degrees, and we know that the friction force is 50 newtons, in this problem we're asked to find all the other forces acting on the sled and find the acceleration of the sled. Now I want you to appreciate something. Last time I gave you the acceleration and asked you to find the forces. This time I tell you enough about the forces that you can find the acceleration. You can use that translator both ways. Now, the first step is to draw a free body diagram. The first force I put on any diagram is the weight. It's 15 kilograms. How big is the weight? I can wait. 150 newtons. And then ask, are there any magnets? No. What touches the sled? The rope, and it pulls. The snow, and it pushes with a normal force and a friction force. Now, the only difference between this problem and the last problem is that when I break up my problem into an x part and a y part, to use Newton's second law, I can't put that anywhere. That's not in the x direction and it's not in the y direction. So I have to break it up into its components. It's 37 degrees, a 3, 4, 5 triangle, so that's 3 times 20, 4 times 20, 5 times 20, or 60 and 80. Now folks, once you break up a force into its components, throw away the original. Use the components. Now, that's the first step. The second step is I get to use Newton's second law twice. In the y direction, I have no acceleration. It's speeding up to the right, so the y part of the acceleration is 0. That means in the vertical direction, this diagram has to scream balance. How big is this normal force? And do not say 150. 90. I've got 2 forces up, I got 1 force down. These 2 forces up have to balance the 150 down. That one's 60, this one has to be 90. Now, in the x direction, I have 80 newtons to the right. I have 50 newtons to the left. What's the net force? What's the scream? 30 to the right. I got 30 more to the right than I've got to the left. If I use Newton's second law, 30 is equal to 15 times A. A's got to be 2. Or if I just plug and chug, I get 2 meters per second per second. Now, your problem is going to be slightly different than that, but the idea is the same.